All right. So greetings, YouTube. Yeah, today was just one of those days. Like all this technology wanted to act up. It's been acting up all day. I barely got my other lectures out. I got them out, but I wanted to do a makeup lecture for this one. So what we're gonna do, I'm just gonna pre-record the video and load the recorded video into YouTube for your viewing pleasure. So for this week, we're gonna continue where we left off. I think we're doing starting with section 1.3 today. Inverse exponential and log functions. The assignment should be on Pearson. I do plan to be available for my office hours tomorrow, so you might have to just reach out to me then. Hopefully, the stuff will be working better, but I'll go ahead and make this pre recorded video and load it and make it available. Let's be ready for exam one over chapter one at the end of this week, and it'll be available on Pearson as well. I haven't gotten full access codes for you all just yet, so you should be able to get temporary access, and I'm working on getting you full access, okay? So, you know, the internet was behaving however it was behaving today. It is what it is. We just have to kind of press forward. So I'm just going to make a pre-recorded video. I'll probably finish out chapter one and then call it a day. I think we have another section after this one, so we'll go ahead and get this one going. So for continuing with chapter one, we have section 1.3. This should be a review from college algebra. We have inverse, exponential, and log functions, and let's see where we're going. So the larger values to be. So we have the exponential function, right? Exponential is where our variable is in the exponent. So values of b will produce greater rates of increase. So the larger your base, the more steep your exponential, the quicker your exponential function grows. So if you look, notice here we have like the base is 2. This is our exponential. Base 3, base 5, base 10, so on and so on. So these higher bases cause it to grow exponentially more quickly. The smaller value to b, the lower. Well, it's like a smaller values to b produce greater rates of decrease, right? So notice when we're at 0.9, it's nearly a flat line, and then at 0.5, we have exponential decay in this fashion, and then at 0.1, we have exponential decay like this, like a rapid decay, right? So the smaller our base is between 0 and 1, the greater the rate of decrease. Okay. So then we have this definition. We have the natural exponential function f of x equals e to the x, which has this base 2.71828, blah, 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 blah. This comes out of a definition. It might pop up here, so we'll see. If it pops up, we'll talk about it. But for right now, this is essentially just a function in the calculator. There is more to the story. We're going to see if it pops up, though. Okay, that's fine. Oh, so on the left here, so if we look at like the exponential function 2 to the power of x, we have the red graph. If we look at 3 to the power of x, we have the blue graph. And then e being a base of 2.7, whatever it was, that decimal. Notice that is between these two graphs. It's between those two, right? The tangent line has a slope of 1 at 0, 1. Right? So the slope of the tangent line here, a tangent line is a line that when we draw it and it touches our graph, it touches our graph once in this fashion. It's not where it crosses like this. If it crosses this way, then that's not what we mean by a tangent line. A tangent line is going to just graze, is going to touch our graph in a fashion like this, right? Okay. So an inverse function, given a function its inverse exists, if it exists, let me see, given a function, its inverse, if it exists, is a function f inverse such that y equals f of x, then f inverse of y gives us x. So if we have y equals f of x, the inverse of y is going to give us x, right? So it's like it undoes our original function. So like if we have a function, the function f takes a mapping of x to y. So we have x passes through this function and outputs our y. F inverse takes that y value and maps it back to x. So it's like it undoes the function. Okay. So a one-to-one function and a horizontal line test. A function is one-to-one on the domain if each value of x corresponds to exactly one value. If each value of y corresponds to exactly one value of x in the domain. More precisely, f is one-to-one on the domain if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. So the horizontal line test says that every horizontal line, the graph of a one-to-one function, intersects the graph of a one-to-one function at most once, right? So if we have a graph, you know the horizontal line test. The horizontal line test tells us whether or not a function is one-to-one, and that means that tells us whether or not the function has an inverse or not, right? So the figure on the left is one-to-one. Notice it passes the horizontal line test. No matter where you draw a horizontal line, it touches it once. But then the function on the right fails the horizontal line test. We can draw, you see this horizontal line here. When you draw this horizontal line, it touches it 3 times. So then that means this function is not one-to-one. Every y does not correspond to exactly 1x. So then it does not have an inverse function. So notice this first example fails the horizontal line test. If we only kept if we only kept the left half of that original graph, that would pass the horizontal line test and similar to the one on the right. So the two graphs on the right are one-to-one because we're only keeping half the graph, but then the one on the left is not one-to-one. What is this? Oh, increasing, decreasing, and constant? Is that what this is talking about? I'm not sure what this image is talking about. Let's see. So notice that the one on the left is one-to-one. Every y corresponds to exactly one x, and every x corresponds to exactly one y. But then the graph on the right, we have a y value that corresponds to 2 different x values, right? So this one is not one-to-one. We have one y value that corresponds to 2 different x values, so it's not one-to-one. So that means it does not have an inverse. So let f be a one-to-one function on a domain with the range R, then f has a unique inverse with the domain R and the range D. This is, let me see. F inverse of f should give us x, and f of f inverse of y should give us y. Basically, it's like these two functions undo each other, and this is how we verify that a function and another are inverses of each other. I think that's the proper way to articulate that. I'm gonna let these be. I'd like to work an example. Can we work an example? Let's see. Let me see. Solve for x. This is interchange and right. Let's see. So this slide is, my voice just cracked really funny. What this slide is sharing with us is that, like, given a function, the graph of the inverse, if we rotate about this line, y equals x, right? So if we consider this line, y equals x, kind of like this. Let's see. Is that gonna let me? There it is. I think that's it. Anyway, if we consider diagonal line y equals x, if we rotate about that line y equals x, we're going to get the graph on the right. Okay. So given the graph, if it has an inverse, we will rotate about the line y equals x, and we'll get the graph on the right. That's what you see going on here. So I kind of want to work an example. I might work some of the homework questions if these aren't going to give us any examples. Let's see. It's kind of repeating. I feel like that's repeating as well. Okay. So yeah, I'll probably just make this one video, and I'll try to get some practice problems or homework problems done. Yeah. So a log function of base b, for any base positive b positive where b is not 0, the log function base b denoted y equals a log. Oh, undo. Y equals log base b of x. The inverse of the exponential function is going to be the inverse of the exponential function y equals b to the power of x. I really want to get to an example. I don't think these slides really do examples. I'll just have to pull for some. And then these are some properties of exponentials and logs, inverse relations between exponents and logs. Because exponents and logs are the inverses of each other, then they essentially just cancel each other out. So a base to the power of a log is just the x, and then the log of an exponent is just going to be the exponent. I'm going to let that be for now. Okay, I kind of want to work an example or two. Let me think about it. Let me at least go ahead. I'm going to stop this recording just for the sake of simplicity. And I'm going to go ahead and do one more section, and I'll take some time to just kind of work through some of the homework as well. That will be a better explanation. It didn't really come with any examples. That's what I didn't like about this, but that's okay. Hang tight.